Our next speaker is Akhil Langer. He's a PhD student here at the Parallel Programming Laboratory. His work has focused in large part on mathematical optimization problems. So the talk right now is on the maximizing throughput of over-provisioned HPC data centers, which he'll explain what that means in a little bit. He also has another talk tomorrow afternoon on stochastic optimization for certain sorts of resource allocation problems under uncertainty. So I'd encourage you to, listen to that as well.
Okay, now we have to it will not come down. Sorry? Yes, good afternoon, everyone. So I'm going to talk about power-aware job scheduling. I'm going to talk about how to maximize performance of a data center under a strict power budget. So as most of us might already be aware of, that DOE has identified 4 key areas where significant research breakthroughs are required in order to achieve exascale in the next decade. And one of these challenges is the power and energy challenge. So the current goal is to achieve exascale in 20 megawatts, and we can see that a lot of a big jump is required in order to do that. So let us see how the power needs of a data center are calculated. So each of the subsystems in the data center has a vendor-specified thermal design power limit, which is the maximum power that any subsystem can consume. So in order to compute the total power consumption of the data center, we just add the TDP of all of its subsystems. The problem with this approach is that TDP of the system is hardly reached. It's rarely reached. But nonetheless, we have to allocate that much of power to each of the subsystems in order to avoid any circuit trips in case the subsystems do reach their TDP limit. However, this is wasteful and excessive because we never end up using that much of power. So the solution there is that if we have an ability to cap or constrain the power consumption of these subsystems, we will be able to add more nodes than what is there in the conventional data center. So basically, the ability to constrain power below the TDP limit allows us to add more nodes while still remaining under the total power budget of the data center. So this is different from how we have been used to thinking, where nodes are usually the limiting factor. But as we are moving forward, power becomes the limiting factor, and the researchers have to start thinking in terms of power. So adding nodes is considered to be economical in this case. So this is what the power consumption of a node on a BlueGene queue system looks like. Most of the power is consumed by the memory. So we'll focus on how to efficiently utilize the memory power, memory and CPU, sorry, both CPU and memory. So we'll look at how to efficiently utilize CPU and memory power. And also there are no good mechanisms available to control the power of other domains. So there have been a family of processors, including Intel Sandy Bridge, IBM Power 6, Power 7, and AMD Bulldozer. All of these allow user to control the power consumption of the CPU through software. For example, Intel Sandy Bridge provides a runtime average power limit library, also called as RAPL, using which one can measure the power consumption of the CPU and also constrain it by constrain it through the software. So let's see how an application performs as the power of the CPU is increased. So the observation which has been made in the previous work is that the application does not perform scale proportionately to the increase in the amount of power. So it might be better for an application to be executed on more number of nodes, each running at a smaller power level, than running on a fewer nodes, each of them running at the highest power level. This is the performance of Lulesh, which is a hydrodynamics application, at different configurations. Configuration corresponds to how many nodes the application is being run on, and what is the CPU power cap and the memory power cap. So this shows that if there is a 1200 watt power budget for a small cluster, then if we are going to run all the nodes at their TDP limit, then we'll be able to have only as much as 8 nodes. But the ability to cap the power consumption, what we are doing here is we are trying to identify what is the optimal configuration on which that application should be executed. So this shows that the optimal configuration is to run it on 12 nodes with the CPU power capped at 44 watts and memory at 18 watts. So given this context, I'll define the problem statement, which is to maximize data center performance. What we saw in the previous slide was how to identify an optimal configuration for a single application. Now in a data center, multiple applications have to be, or multiple jobs have to be executed simultaneously. So the problem is to maximize the data center throughput or performance under a strict power budget. So we assume that the data center has these capabilities. First is the power capping capability. The other is over-provisioning. And optionally, the jobs can also be either moldable or malleable. By moldability, we mean that the user, instead of specifying a single node count on which the job should be run, he can specify a range of nodes, and the scheduler will pick one of the from some node count within that range and execute the job. However, the job's configuration cannot be changed while it is executing. In malleable, we can actually change the job configuration even during its execution. For example, we can increase the number of nodes or reduce the number of nodes. So this feature already exists in Charm++, in which it just adaptively redistributes the compute objects to the new set of processes. And it has also been tested in MPI, such as dynamic MPI. There is some work for malleability in MPI jobs. So this is a very high-level overview of the power-aware resource manager. We also call it as PARM. So first of all, I'll cover two major components in my talk. One is the job profiler, and the other one is the scheduler. So let's look at the job profiler first. So in the job profiler, it is basically responsible for predicting the performance of the application with power. So what we do is, first of all, we measure the job performance at selected CPU power caps and number of nodes. And then we use a power-aware strong scaling model, also called as PAS, to predict the applications or the job's performance at any scale. So there have been a lot of work in the previously work in which we predict the execution time as a function of the number of nodes or as a function of frequency, but there has been no work on how to predict the execution time as a function of power, because this feature didn't exist earlier. So we use the existing strong scaling model, which predicts the execution time as a function of the number of nodes and the average parallelism in the application. Then execution time can also be modeled as a function of frequency. Here what we see is that beyond a particular frequency, the execution time does not change. And before that threshold frequency, the execution time is a function of the amount of CPU work and the memory work. In order to model frequency as a function of power, we have three components here. First is the dynamic power of the core, which is a function cube of the frequency, and then the rate at which the application accesses the caches and the memory. And the third component is the static power of the CPU. So we use all these three models and combine them, and we get time as a function of power and number of nodes. Now this performance characteristics of the job are passed on to the scheduler, which then all the equations are messed up. I will need them actually. Okay, I can just go through them like this. Basically, there are 4 sets of constraints here. One of them just it's an integer linear program formulation for scheduling. Basically, it selects the jobs and also decides at what configuration to run each job on. So each configuration consists of the scale and the CPU power cap for the job. So in one of the constraints, it's just to select the jobs. This bounds the total number of nodes which are available in the overprovisioned data center. And then these sets of constraints, this set of constraints bound the total power consumption of the data center. So for non-malleable jobs, we make sure that the new decision does not change the number of nodes what it was before the scheduling decision was made. So what is more important in the formulation is generally maximizing throughput of using a integer linear program is a computationally very expensive problem because it's an integer linear program, and it's not feasible to do it for online scheduling. So what we do is we take a greedy approach. Instead of maximizing the throughput, we maximize the sum of the power-aware speedups of the jobs that are selected for immediate execution. So this is how we define the power-aware speedup of a job J at nodes N and power P. It is defined as the ratio of the time the job takes on the minimum number of nodes and the minimum power cap to the time on number of nodes and the number of and the power at which we are measuring the speed up. So this basically makes it feasible to solve the integer linear program for online scheduling. So once the scheduler makes these decisions based on the ILP optimization, it is sent to the execution framework, which is responsible for ensuring the power caps and also shrinking and expanding the jobs. So for the experiments, we took a wide range of applications varying from memory intensive to computational intensive. We use these 2 applications which are memory intensive, then LeanMD, which is a computationally intensive application, and then AMR and Lulish. These are both computationally and memory intensive. For our testbed was a 38-node Intel Sandy Bridge cluster, which has power capping using RAPL. And it allows CPU power capping range from 25 to 95 watts. And for the job data sets, we generated 2 data sets with each data set having a different CPU sensitivity. One of them has a low sensitivity to CPU power, and the other one has a higher sensitivity. So we assume that there is a budget of 3,000 nodes, which enables us to power only 28 nodes out of these 38 nodes. But in the overprovision, we assume that there are 38 nodes available. So first of all, we measured the accuracy of the power-aware strong scaling model. And an important thing that note here is the CPU sensitivity. We can see that LeanMD, which is a computationally intensive application, has a high CPU sensitivity, and others have progressively lower sensitivity. This shows the modeled, these lines here show the performance predicted by the model, and these markers here is the observed performance. So we can see that the model is predicting fairly accurate performance of all the applications. To compare the results of the scheduler, we compared it with the Slurm scheduler, which is used in most of the top supercomputers in the world, in many of them, not most. And then we compare Slurm's performance with 3 versions of PARM. First one is called as NoMM, in which the jobs are neither malleable nor moldable. And we get an improvement of 32%. Then we increase the degree of freedom by allowing the jobs to be moldable. And then we get another 13.9% improvement in that. And finally, we also allow all the jobs to be malleable, which adds another degree of freedom. And then there is a 7.5% improvement with the WSE, which is the 3rd version of the PARM. Overall, there is an improvement of 1.7x in throughput. So these were the results with a relatively small scale cluster, but in order to predict or in order to analyze its benefit for a large scale cluster, what we did was we compared the results of Slurm's simulator with PARM simulator. These simulators are nothing but just wrappers around the actual schedulers, which instead of actually executing the job, they just jump to the next trigger when the decision has to be made and then give their decisions. In order to make the prediction more reliable, we also modeled the cost of shrinking and expanding the jobs. The cost of shrinking and expanding consists of 2 components. One is the boot time of the nodes, and the other one is to transfer the data to the new set of nodes. These are obtained from the interpret data, and this is just modeled as how much time it takes to move the data from the old set of nodes to the new set of nodes. For these setups, for this experiment, we used job traces from interpret. We chose 3 subsets of from the interpret job traces, each having 1,000 jobs. Since the power characteristics of these jobs was not available, we chose the model parameters randomly from the applications that I showed earlier. Because these applications are from they span the range of both computationally and memory intensive. We believe that these parameters are well representative of all the real applications. Now, these job traces only specified a single node on which the application has to be run. To get the range of nodes on which the job can be run for malleability and moldability, we just multiplied that node number with a constant, varying in the range 0.2 to 0.6. And there are 40,960 nodes, which corresponds to a total power of 4.75 megawatts. So this is the performance of the baseline, which is the Slurm scheduling with the other 2 versions of PARM, the one which only allows moldability and the other one which allows both moldability and malleability. And these are different data sets. For what we did was to get more diversity in the job arrival rates, we multiplied the arrival rates in these data sets by a factor of gamma. So as we decrease the gamma, the job arrival rate increases. So we can see that the performance of PARM does not worsen as much as the performance of the baseline in all of these data sets. And in the best case, we achieved up to 5.2x speed up with the WSE version of PARM. Now, a question that is raised is most of this benefit is probably merely coming from over-provisioning of the nodes. But in order to prove that that is not true, there is merit to actually doing intelligent power allocation using the integer linear program formulation. We did this experiment. We compared the performance of PARM with a naive strategy in which we fix all the nodes at the same power instead of letting the scheduler decide the power. And we can see that in almost all the different powers at which the nodes were set, we get significant speedups. And yeah, so when basically this 30 corresponds to the situation in which all the nodes are capped at 30, and given that there is a power budget of 4.75 megawatts, there were a total of these many nodes. But our strategy, the PARM, it gave a speedup of 4.32 over this naive overprovisioning strategy. Finally, the conclusion is that significant achievements in throughput can be obtained by using power-aware scheduling. And the power-aware scheduling basically requires to have a power predicting model and then CPU power capping and over-provisioning of the nodes. Sophisticated ILP scheduling methodology is useful for obtaining better performance. And adaptivity in the runtime systems, which allows malleability, further improves the benefits. But the approach can also be used for non-malleable jobs. There's a lot of interesting future work that ensues from here. First of all, similar to reducing the power of CPU or memory, we are also considering enabling and disabling caches, because the amount of power that caches consume is significant, but the performance benefit might not be proportional. Thermal constraints, we are planning to introduce thermal constraints because thermal temperature directly decides the reliability of the machine and the cooling power of the data center. And finally, we'll also include bridge support for user priorities. Thank you.
So let's thank our speaker, and we can take any questions.
So for the malleability, and I may have missed this, did you consider the possibility of individual cores choosing different frequency, or at the socket level?
No, this is at the
node
chip
level.
Yeah.
The chip, but
chip may have multiple cores, and
yes, but the node often has multiple chips also.
Yeah.
Like multiple.
So each chip has its own power cap.
I see. And did you consider like different chips in the malleable case? Different chips having different power caps?
Yeah.
Okay.
Actually, there is only one chip in this case, which
Okay.
has 6 cores. So
I see.
But yeah, power can be controlled at the chip level.
Yeah, that's what I'm saying. So for the adaptive runtime, you know, where there can be all kinds of possibilities. If things are getting more memory bound, there can be, you know, when there are many cores. We're envisioning 1,000 cores on in a node, and that's definitely going to be more than one chip, I think.
Yeah. So right now we are assuming all of them.
Yeah, I'm just thinking. I see.
Yeah,
I see, right. And in the future, there may be more opportunity. Yeah. Right. Right. But I think in the future, the hardware will allow, you know, more efficient power control too for the individual cores. So one could push this further. Yeah.
Okay, we've got time for one more question.
What are you basing the, there's a large amount of discussion going on right now that temperature sensors on the processor in the core or the uncore don't seem to correlate very well with reliability. So it's kind of well established for disks that they need to run at their kind of right temperature, but it seems like a lot of the data coming out of the data centers now, particularly the LCF centers, that it's not temperature that kind of determines. It's something about, it's the age and the kind of duty cycle and the kind of the, you know, what kind of instruction mix the thing's getting. So is there kind of recent work that kind of shows temperature to reliability on current processor platforms?
Yeah, there has been recent work. I don't know about the details, but that shows that reliability is directly proportional to the core temperatures. Maybe.
So basically, this is not related to this part, but last year we had a paper about improving reliability through temperature control. And I think what you're saying is, but that's not, maybe temperature doesn't really increase reliability.
Well, yeah, or the inverse, right? I mean, maybe controlling temperature is related, you know, it correlates, but maybe it's not causal. Like it's not failing because temperature went up, but maybe temperature went up because, you know, this product's just wearing out for some reason. There's something, it's not predictive. That's the part, you know, when temperature is going up, you gotta kind of run away fast. Whereas it might be that there's something more kind of historical about the processor that tells you more about it's going to go belly up. Yeah, so there's a very high temperature. At very high temperatures, yes, you start getting these kind of solder joint failures and latching failures and things like thermal issues start, fluctuations kick in. You don't latch properly. But anything below that, it's a very nonlinear response, it seems. So, I've heard it since I worked at Bell Northern Research, the exact same thing, and everyone just cites another paper, which cites another paper, and it's very hard. From when we used to do the shake and bake at Northern Telecom, the temperature didn't correlate with reliability, and so we just cited other people and carried on. But we might want to find original work on this or redo the experiments, like take a current set of chips and just let them. Yeah, well, let's go do it, and if it exists, let's publish. Please.
Okay, let's thank our speaker once again. Okay, and our third and I believe last speaker for this session is Suraj Prabhakaran from the German Research School for Simulation Sciences.
Thank you.